also have wi. So this is xi, this is yi, and the size of the dot, I use the size to encode the weight. This has a weight of 4. Si equals 2. Si squared equals 4. Okay? And all the little dots, they have weight of 1. Okay? So you can think of, I observe this, but for these 5 points, I have larger weight, and I want to do the weighted least square. So this is how I generate the data. The gray line is the underlying fixed model. I assume it lies on this line. I sample the X domain evenly, and then I add some IID Gaussian to it. Okay? And then I just pick these points, these 5 points for larger weights. If I just perform least square on these points, so the weights are ignored, this is how, if for this particular line, I will calculate the prediction error. This is yi minus wxi. This is the absolute error, but it's square, so I give this square box. Okay? If it's weighted least square, what it means that even though this is my error, yi minus wxi, remember this has a si equals 2. So it's actually, it's not going to be, I'm not going to use this as my error. This is going to be middle of the point. The error I'm collecting is 4 times larger. Instead of this, I have this to work with. Okay? So what the weighted least square, the approach is telling us, this is equivalent to weigh the points. Instead of x, I'm going for xy, fit this. I'm going to fit s times xi and si times yi. Okay? So all these points, they have weight of 1, so they stay where they are. The red circle is the scaled version. This is the red circle is the scale version. The black points are the solid points, are the original points. You can see those with the weights of 1 stay where they are. Like this red circle. This is a point and they stay where they are because when si equals 1, they're the same. For those that, for example, this point, it has a larger weight. Si equals 2. So it's gonna be this, if I connect from the origin, it's gonna be twice. It's gonna be located to this point instead. Okay? For these 5 points, they expand outward. Okay? So instead of looking at these black points of different sizes to illustrate this weighted least square, effectively, I'm dealing with the least square problem on these red circles, equal weights. Okay? And you can see that the green line actually is the fit from the black points. It's a least square solution, ignoring the weights. The red line is the weighted least square solution. They are not the same. When you change your criteria, the solution is no longer the same. Okay? Okay. At this point, I actually have a question for you. Let's say that you have written least linear regression on nonlinear features. Okay, you treat this as a black box. Okay, let's say even polynomial regression. You call it function. Actually, it's a real function in MATLAB. So polyfit, okay? And this will take x and y, right? Your points. Now you have your problem x, y, and you are given the weights, y, the w, or just to be consistent, let me make it s squared, okay? xi, yi, si. Okay? From what you have learned, weighted least square is just least square on weighted data. Okay, so this actually take another parameter called p. What's the order you want to do, right? Yes? Now, how would you call this function to get your new weighted least square solution? You want to do weighted least square on these points. You have already a function written based on least square solution, polyfit, okay? And it takes x, takes y, takes the order p you specify. So how would you call this function to perform weighted polynomial regression? So let's say, so these are the points, okay? The raw points. So let's say it is, even just go for 1D, okay? x1, x2, xn. And you have y1, y2, yn. Okay? Now you have another vector which is s1 square, s2 square, and sn square. Yeah. The thing is, I want you to use the existing function you have already written. How would you do it? So this version, okay, can I just do something like that? S times x, s times y, and a p. Yes? Yeah. Anybody say no? One? Oh, there are a few of them. Who would like to articulate the reason? Yes?
Uncertainty in the higher order terms is going to increase, right? Because you're multiplying uncertainty in the higher order ones. So it's not just going to be the s.
So his answer was the uncertainty for the higher order terms will increase once you take the higher order terms. That's a great way of looking at it. You really understand, the uncertainty increases when you have variable x. You go for x2 squared. You can think the distribution will change, the uncertainty will change. But I have another way of looking at it in terms of optimization. Remember least square regression, going for a polynomial, essentially is turning the feature into nonlinear features, right? So it is linear regression on the nonlinear features. So the feature could be taken E, so could be P0x, P1x. Sorry, P is not good, but P is order x, right? And this you are solving for the W. So if this is my feature H, what this weighted least square says, instead of solving this problem, I should just scale S of H. I should scale the nonlinear transformed version, not within the variable itself. Yes? So make it, what this says is, even if I just do two terms, x, two terms, what I should do is, this is my nonlinear feature, right? I should do s times h, so it becomes s times x, s when you call polyfit Sx, so Sy, so on and so forth, yeah? You see the difference? So least square going to weighted least square, the concept is straightforward. But when you make the extension to nonlinear regression, linear regression over nonlinear features, you have to be careful with this. This still holds, but only on the nonlinear transformed feature. You should apply the scaling to the nonlinear transformed feature. Okay? Okay. So let's take this a step further. Instead of individual, still independent noises, we actually have, instead of this, we actually have dependent noises. When would we face such data, such noise models? For example, for time series, you have correlation in time series. This is just a very simple model. It says, so the I can be interpreted as a time point, I plus 1. At the time I plus 1, that noise is not completely random according to this function. It is this, but it has this, this residual effect from the last noise. The last noise was Zi. The previous noise decayed a little. Let's say it decayed by a factor of half, okay? If the last noise is large, let's say 3, this will get 0 times 3 plus additional independent noise. That's how the measurements from one instant to the previous instance gets correlated with each other. Another example is sliding window average, also called moving average. You are taking, your measurements is not the raw measurements, but it's the sliding window average. You calculate, you have 10 measurements, you calculate the average measurement within this, among these 10 instances. You move one step. So first you're calculating the number 1 to number 10, you calculate average. Then you compute number 2 to number 11, what's the average? You can see that they share, point number 2 and the number 10 are shared between these two averages. So they are correlated. And one way to capture this correlation is assume the noise at I plus 1 is correlated with the previous k steps, okay? So these coefficients, these are, again, they are still linear models. These are fixed, and these are independent IID noise, okay? So you have some variable which are independent, but you model the correlated noise by the linear combination of these IID noise. As a result, your Zi becomes correlated over time. So in general, we can represent the noise vector as Z equals a linear combination of some independent IID noises, okay? And you can see that when we were dealing with individual noises, we are already looking at each instance, one noise model. So earlier, the noise is only lives in the feature space, D-dimensional, right? If you have D measurements, each target value has D values, your noise is D-dimensional. Now, when you are dealing with individual model, individual instances, each instance has a noise model. So the dimension becomes N. Okay, we are still dealing with scalar target value, so this D equals 1 in this case. And the A is N by N. N is a IID Gaussian, okay, for each point. Z is called a jointly Gaussian random variable. Now we need to figure out how to derive P of Z. What is the probability of Z when Z is a jointly Gaussian random variable? It could be jointly Gaussian variable, but if each instance independent of each other, we know that it's just, just each is Gaussian. So, if the covariance matrix will be diagonal matrix, very easy to handle. But what about a generic jointly random Gaussian variable? This is when we talk about the Gaussian noises. I want to review what we have learned. One important property is the linear combination of Gaussians. If N1 and N2 are independent Gaussians, have their own mu1, sigma 1, standard deviation, the first two moments, then their linear combination, the mean is just a linear combination accordingly, and the variance are also weighted average. The weights are squared before they are averaged. So let's write this out in terms of matrix algebra. If I represent these two as a joint random variable, then the mean is just mu1, mu2, right? One for this N1, one for N2. The sigma 1, sigma 2 is their variance. This is a covariance matrix. And this is 0. The cross term is 0 because they are independent of each other. Okay? And we denote this as mu and sigma. So this is my the mean of the joint variable, and this is the covariance matrix, usually denoted by sigma. Okay? And this is the n. Z is a linear combination of the two, and we can write it out as this row vector times this column vector. Okay? It's a very specific form. And this becomes a one scalar. Okay? In general, it's this form. So now we know this A1 mu1 plus A2 mu2 can be written as A1 A2, a row vector, times mu1 mu2 as a column vector. That gives me this, right? And this covariance matrix can be, it's a proper quadratic form, right? Quadratic form. And it's just this diagonal takes a sigma 1 square, sigma 2 square. This is if Q is my quadratic form matrix, xt transpose x is a quadratic form, right? Diagonal term correspond to x1, x1, x2, x2. The off diagonal correspond to, it's just this correspond to x1 square q11 plus q12 x1 x2 plus q21, sorry. Anyway, it corresponds to q21 x2 x1 and plus q22 x2 squared, right? That's the linear algebra quadratic form. So this term can be written as this quadratic term, and that is just this A mu, A sigma, and A transpose. Okay, that's the form of it. So if Z is a linear combination of n, here n assumes IID, then the mean is equally transformed. The covariance matrix is transformed in this quadratic format, A sigma, A transpose. Okay? This is what we know already, right? I'm just rewriting it in terms of matrix algebra. Nothing new. And we will learn that for the d-dimensional Gaussian random variable, its probability density function takes the following form. Okay? Here you have the determinant of sigma, the covariance matrix, and the square root of it. And here you have square root of 2 pi but the raised to the power of g power, and this is what we know of already. It's quadratic form, taking the mu as the mean and the sigma, the covariance inverse as the dividing factor. And if you, there are two special cases. When d equals 1, this is what we know of. In fact, it should be just this, and be simplified, because sigma just becomes sigma squared. And if d equals 2, and we can, d equals 2, it takes, the general form is this, but if it's diagonal, it's IID, it's this form we know of. So let's look at some examples. This is a 2D Gaussian, modeling independent, identically distributed Gaussian. The sigma and the two axes is identical, 9 and 9. So the sigma essentially is 3, okay? According to the 3 sigma rule, this is from minus 9 to 9. So you can see that beyond the 3 sigma is more or less gone. The bump has already vanished almost to 0. And the value of this function is color mapped. The hotter, going from blue to yellow, it becomes larger. So again, if I take these 2 points, so this is a sheet, it's a surface, but since it's color coded, I don't need this 3D plot. I just need a 2D plot. I pick the sheet and lay it down in the 2D plane. Just by looking at the color, I know the density. This is what we already know very well, contour maps, these iso contour maps. These 10 bright circles indicating the even spacing from 0, 1 all the way to 1, for example. In the normalized, the peak is normalized to 1, okay? So you can see that for IID Gaussian, it's isotropic in every direction, equally likely, okay? The center is mean at the 0, so the center is 0, 0 is most likely value, and all the way falls down naturally. And if I sample, so this is a PDF, if I sample 2D points according to that distribution, here I have 1,000 points. I literally sampled 1,000 points, and that's the distribution. Because see, as you go to the outside, there are fewer and fewer points, very sparse points. In the middle, a lot of density. There are probably a lot of points overlaid onto the same, each other, so you don't feel like it's 1,000 points, but it is actually 1,000 points. And this is the so-called individual noises. In X dimension, the sigma is 3. In the Y dimension, the sigma is 2. So this, it spreads out more. This dimension spreads out more than this dimension. It's a little squashed in this way, okay? This is what it looks like in a contour map. It's much easier to see. It means that, you know, the X value are gonna vary to a greater extent than the Y direction. But they are independent of each other. It means whatever I take this point, you know, has nothing to do with X. You know, there's an X value, but the Y value, this probability has nothing to do with X. Okay, they're independent of each other. Okay, so this is what we know of, right? We have already talked about linear combination IID noises. We talk about weighted least square where I have individual noises, but they're independent of each other. Now we want to get to this generic dependent noises. I want to deal with cases where here this is no longer 0. There's some off-diagonal terms, cross correlation. So how do we derive, you know, we have this Z A times N. I know the form of IID Gaussian noise. It doesn't matter how many dimensions I have, the probability P of n, if I have k variable, it's just P. It's the product of these variables. If they are independent of each other, and each is a very simple Gaussian function, it doesn't matter how many dimensions I have, I just make a product of these isolated probabilities, right? That's very simple, straightforward. So in general, if I have a function of some known variable, how do I derive P of z from P of n? Okay, we know the form of Gaussian already, but in the next few slides, I want to show you how do you derive such probability, because your function may be different, but the methodology is the same. How would you derive a probability density function from some transformation of known density functions? First is so-called this Riemann sum of density function. When you want to do integration, right? The probability n is the known variable, random variable. N belongs to some source in the source domain. It occupies some area. This is a probability that the random variable n falls into some disk source domain S. Okay, and we want to calculate the probability, right? As this area becomes smaller and smaller, I get the density, right? So that's intuitive how you're going to do it. And so by definition, this is the density. I have to integrate the density over this area, and this can be discretized using a Riemann sum. So essentially, it's density function. I quantize it by this grid. For every grid cell within this area, each cell will have some value. I just use this value within the cell and times this area. So this will be delta n1, delta n2. So this time together gives me this area. So I'm using this piecewise constant approximation. The probability over this disk is each grid cell. I assume it takes the center value, and then I multiply this by this area. I add them together. It should approach this value when the grid becomes finer and finer. That's just, very simple differential concept. Now, this is the variable n in the source domain. I have some function z. It's a linear transformation of n. So every point in this source domain, you can find the counterpart, some point in the target domain. It's one-to-one mapping. So because it's one-to-one, every event happening, the probability of n falls into this area is the same as the probability that the z falls into the target area, right? Otherwise, it's not a one-to-one mapping. Yes? So that's one equation we have. And then the linear transformation. Now this square grid cell in the linearly transformed area, it becomes this parallelogram, and the area of this parallelogram is the area of the square multiplied by the determinant of A, taking the absolute value. Depends on how each column of A is taking whether you take one column or minus that column, determinant may have negative value, but it doesn't matter in terms of the area calculation. So you take the absolute value of that, which means that each cell you have delta Z1 and delta Z2. This area is calculated as delta Z1, delta Z2. and this is delta n1 times n2. So this equation leads to this. Delta z1, delta z2 equals this factor times delta n1 times delta n2. So now we want to relate the before transform PDF, the probability before the transform to the probability after the transform. This is written as such, as a Riemann sum of delta n1 variables. And this is, by the same token, it's really, I denote the probability over, for z denoted by q, but they mean PDF is the same, but just to keep, to differentiate them, I use q. Now, I want to relate them, so but z1 is according to this transformation. Z is a times n. So I can rewrite this as a times some n, right? And this is this change of variable. You have to make it consistent. If this variable changes to be expressed by n, likewise the area, the differential quantity should also be changed to this based on the previous line. And now if you compare these two, these are equal. So these cancel out, and this you will have Pn1, N2 is just Pn equals Qan times this determinant of A. In this case, N map to Z through linear transform A one-to-one mapping. You can totally do the other way, completely, because if Z equals A times N, that means A equals A inverse of N. This is again is a linear transformation. So you can derive this as well. Q of Z is P A inverse of Z. The DET of A inverse equals DET A inverse. That's just the identity for the determinant, okay? So now we have, so through this exercise, we learn how to, usually you might think, the transformation, if the Z is related to AN, you would have thought, usually you would have thought, PN equals just QAN, right? You just replace the Z, this is Z. You just make it AN. This you need to be careful. Today is this problem. Another day is different problem. This is to show you when you do the change of variable, you need to be careful. It has to be consistent with the quantity when you express the integrator as well as the differential variables. Okay, now we have this equation. We know that the after transform, the probability density is related to the previous probability density function. If we take the Gaussian as a special case, so this just copy over, just one scalar constant. This thing, because the n, so this is just becomes, because they are IID, n is IID, n equals A inverse Z, but n each is independent of each other. So the probability, the joint probability of that is just the product of these individual probabilities, okay? This is just to say, I'm getting the n in general is this, but the ith variable is just this, take the ith row of that, okay? That's what this means. It's just that. And now, each ni is just a scalar, just a one-dimensional variable. It's just simple Gaussian. And so essentially you have A inverse Z1, some Gaussian function, right? Some e to the minus 2 sigma squared, plus, so the dot product, multiply another one, A inverse Z 2 sigma squared, because they are multiplied together as exponential function, it corresponds to these terms add together. So it's A inverse Z1, sorry, Z, the first term, square, plus A inverse Z, second term, all the way to the nth, A inverse Z, nth term, square, divided by sigma square. And since you're adding all these terms together, it is simply because n inverse Z is just n vector. It's n times one vector. It's just the dot product itself. So you can simply represent it as this. And if you spell this out, it's a Z transpose A inverse transpose A inverse Z. So you get to this. And then you do take the inverse, common inverse out, it becomes AA transpose inverse. That's it. Okay? So we have this, we just copy over. We know that since n is RID Gaussian, the covariance, it's a zero mean, it's noise, it's always assumed zero mean. The covariance equals this n transpose, this identity matrix. So if we calculate ZZ transpose, since Z equals AN, we just plug that in. And since A is a fixed constant, we can take it out of the expectation. Since this is an identity matrix, we just derive the EZZ, the covariance of Z is simply AA transpose. And the determinant of sigma Z then becomes determinant of AA transpose. And the determinant of the two matrices multiplied together is a determinant of individual terms. Determinant of a transposed matrix, this equals DET of A itself. So then it becomes DET A squared. Okay? Now we have dA is simply, this thing is just square root of this guy, right? So we are gonna have, since missing a square root, and this AA transpose we're gonna rewrite as in terms of sigma Z. So that completes the proof. For n-dimensional generic Gaussian, we start from very basic RID Gaussian, each just a 1D, one-dimensional Gaussian function. From this is a 1D Gaussian, okay? Just from this fact, this is a 1D Gaussian distribution. I know that this is defined. I can derive any multivariate Gaussian generic form. It should be this. This is a key concept. You model it as RID Gaussians through linear transformation. That's how you expand and derive some more, you build up a more complicated multivariate Gaussians. Any questions? Okay, since we have that, let's continue our example. Now we can actually handle this. I'm introducing cross-correlation term between x and y. It's no longer zero. Okay, you can see this Gaussian bump has turned a little. And in the contour map, it's much more clearer. Okay? Initially, when I have 9, 4, this 0, 0, it's upright ellipse. When I introduce off-diagonal term, it rotates. Okay? And if I sample 1,000 points from this, this is what I get. Now, we are talking about colored noise in the measurement space. It's not in the domain X, it's in the target value Y. If we have a 2D colored noise, we are talking about target value has 2 dimensions, Y1 and Y2. If you pay attention, So this is Z1, Z2 because that's noise. But the Y is some X to be modeled plus Z. So if Z is 2 dimension, meaning Y has 2 dimensions, right? So what I plot here is, so in my Y1, Y2 space, Y1, Y2 space, okay? These are just measurement space. I sample some grid point. These are the values in that space. Right now, there's zero noise, no noise whatsoever. So if you get this measurement, you just take a value from each of these gray points, okay? It's good to see them together. If I add this one, this is IID noise. The noise is 99, okay, so sigma equals 3. So what I'm doing here is actually what I plotted here. You still see, for example, take this point. You still see the original gray point. You see this gray point, the source point. I have my Z1, Z2. I'm gonna add this vector Z1, Z2 as a displacement to this measurement, and I get this green point. The green point is this initially noise-free ground truth value corrupted by IID noise, Y noise, okay? This is what you get. This is what you actually get after the noise corrupted the source point, okay? So if you look at this plot, overall you can see that each line, each red line, visualize Z1, Z2. And if it follows Gaussian distribution, it means most likely they're 0, 0, right? And then it falls off. It's isotropic. Every direction is equally possible. There's no differentiation of horizontal or vertical. You can see all these lines going in all directions, and the length sort of kind of even out. Yes? Okay? In contrast, if you look at 9 and 4, this is individual noise. It's still Y noise, but each dimension has its own noise level. X dimension has more noise than Y dimension. First dimension is more than the second dimension. Okay? Horizontally, you spread out. You can see there's more horizontal line. By and large, there are more horizontal lines. They show up more in a more salient fashion. Yes? And the bottom of this figure, I have cross correlation. If you squint your eye, essentially you see some kind of slanted line like this overall, on average. Yes? So remember, colored noise is in the measurement space. It has not changed. You know, if I could, I will show you, plot at Y1. I could actually. At Y1 and Y2 can be derived from X, from single variable. So I still have a 3D plot to show. But the X is fixed. There's no noise. It's just in the measurement space, I add some perturbation to the ground truth value. The color noise just showing that statistically, over each point will have some random noise. Statistically, there's some correlation among them. For Y noise, there's no correlation. Each point can be considered, infested with same kind of noise all over again. But for the colored noise, there's a correlation. If the first dimension has certain value, the second will have a correlated component. If it's large, the second will also correspondingly large. That's what it means. Okay? If the first noise and the second noise is completely independent of each other, the first one is large, the second one can be very small. Or could be large, doesn't matter. But when there's a correlation, if this component is large, that will also have fractional, a proportional amount to it. That's what it is. Okay. now we handle dependent noise. We have a noise model. How do we derive the, when we have least square, we are talking about ID noise. When the noise are independent but individual, we have weighted least square. When the noise is dependent, it's generic. We call it the generalized least square. So essentially, the noise model, it's the X weighted by the Z. Z is now generic. The covariance matrix is any sigma Z. And then the Y, because X is considered not a random number, just data. Here, so we are kind of mixing something together. Remember, in the probability theorem, the random variable itself is capitalized. The realization of this is usually noted by lowercase variable. So this is to show these two are random variables. But X here is actually not a random variable. It's just domain variable. But we are taking this as this data matrix n by something, n by d. Okay, so Y, this thing is deterministic, and this is the randomness caused by the noise added to it. And then, since now we have an expression for the generic Gaussian noise, Gaussian model, we just plug that in. That becomes this and this. Okay, sorry. And then these has nothing, even though they look complicated, but this has nothing to do with, again, nothing to do with W, so you can take them out. And essentially, the max of this becomes X min of this. Okay? So there are a few different ways to derive the GLS solution. The almost foolproof way is to go by SVD. We need to do the SVD of this covariance, the inverse of the covariance. The covariance we can decompose into the SVD. Since this is covariance is symmetric matrix, it will become, U SU transpose, and this we can write it out as this sigma 1 square, sigma 2 square, so on and so forth. So we can introduce this this diagonal matrix, each correspond to the standard deviation of each variable. Excuse me. Then this simply is U S minus 2 U transpose. So now we just turn this criteria expanded by this SVD, and this can go with this the right side, and this can get into the transpose by transposing itself once, and once you take the transpose again, it becomes U. Now this is identical, and this is just the S minus 2. So this is essentially a diagonal matrix. This leads to the WLS we know of, right? This is a diagonal term. It just weight each term by the S minus 2. And if you turn this into S minus 1, give 1 to this and give 1 to this side, you essentially have this term. So GLS can be understood, can be solved in 2 steps. The first step is turn initially xy into U transpose X, U transpose Y. It's this equation, going from this to this. Because U, if I know the sigma Z, I can calculate the eigenvectors, the singular vectors, it's the same. So this can be calculated, these are all known. First, when you do this, essentially the noise model becomes, the WLS, the individual noise model, they become independent of each other. So it's noise decorrelation. Each noise dimension is no longer correlated. For the Gaussian case, it also means they are independent. because Gaussian is only specified by the first two moments. And then the second step is we still have the S minus 2 to take care of, and that's just the weighted least square on this data. Weighted least square on U X U transpose Y with the weights of S, with a scale of S. And that, as we have learned, is simply least square on scaled data. Okay? Okay, so that's, but here, U is n by 1. It's not, we are not denoising in the d-dimensional space. Right? D-dimension is in the x space. In the y space, you know, that's what we have. We are adding the noise to the y, not adding the noise to x. Another way of looking at this is to, initially you have sigma z inverse. I'm going to split it into two equal terms. Okay? minus half each. If the SVD is this, the half of it is simply, it's this half, the middle term half, that becomes minus 1. And so you can see that this equals this, okay? And this equals sigma. This is the symmetric matrix, so it equals the transpose of it. So since this equals transpose, this term can go to this. You apply transpose once, it equals itself, so with this or not, it's the same. So then, essentially, I can complete the square. So this is just some vector. This vector multiplied with this vector, transpose version times this, essentially is the L2 norm of this vector. So, and this is a known matrix, so I can multiply inside this bracket. And so essentially I have, you know, sigma minus half times y and sigma minus half times x. And this, in a way, you can think of, after I apply this transform, the data completely whitened. The noise model is IID and a union norm, the standard deviation of 1. Okay, it's a different way of looking at this. And we can verify this is equivalent to what we reached earlier, because sigma minus half is simply US minus 1 U transpose. So we just plug that in, we get this. But U is orthonormal matrix. Orthonormal matrix does not, you know, equals this thing. You can take this out, it's common. Orthonormal matrix just apply rotation to the matrix. It doesn't change the length of the vector. So it can take out, you know, it doesn't matter. So that becomes this. And this is what we reached earlier. Okay? It's just a different way of looking at this. But from this perspective, you can think of GLS solution is simply applying least square solution on whitened data. The whitening matrix is the covariance, the half square root of inverse square root of the covariance matrix, whitening matrix transform. Okay? So I have some colored noise. I can whiten it. And this, with this data, the equivalent noise model on the transform data is RID. And with the unit Gaussian models. That's what it is, simple enough. Okay, so that's a part we have dealt with individual noises. We extend to colored noises when there's correlation among the data. And now we talk about the random weights in the model space. In the ordinary least square model, we maximum likelihood estimation views y as x weighted linearly and add some, this is fixed, but add some Gaussian noise. The ridge regression, this is considered a random variable. That's why we use uppercase W. We assume W follows some Gaussian distribution. Okay, that's why in the ridge we have the data term plus this term. Okay. Now, instead of this IID model for the weight space, in the weight space, we are going to extend it to any general Gaussian function, Gaussian probability density function. Okay? And what does that mean? Initially, my prior model on the weights, for example, slope and intercept, each is a Gaussian. And each dimension they are this, same distribution, isotropic. And this says that maybe the slope and intercept they are correlated. If the slope takes 1, maybe the intercept somehow goes, has some correlation with it. It's not completely random. So if you have such a prior belief, you want to use this generic Gaussian to capture that. Okay? So, okay, this is third time we see this reparameterization trick. First one is with weighted least square, right? We just model individual Gaussians as IID unit Gaussian multiplied by constant sigma I. Then we saw it in color noise. We turn into this z equals a times n, linear combination of IID noise. In this case, likewise, we can reparameterize W in terms of IID Gaussian V. Okay? Of course, the weight, you might have some prior belief, the mean weight. So it's a more general. So it's some linear transformation of some IID Gaussian plus this linear transformation, and then you have this mean. And this is your generic Gaussian PDF. Now, if W equals this, I have a change of variable. Y equals xw plus z becomes y, x, and this, you plug that in, you get this. And you can collect the term. V is the random variable, z is a random variable. And it becomes, and you can move this constant term. This is constant. You can move it to the left side. Now this V is IID, Z is IID, Z. So then, if it falls to this thing already know from ridge regression. In ridge regression, if x and y are domain variable and a target variable, then the solution is simply x transpose x plus lambda I inverse times this. In this case, my x is this transformed version. Y is this, again, modified version. So I just plug that in. So I just apply this ridge solution to this data with this x and with this target value. Okay, I just plug that into this equation. This x becomes this, and the y in the equation 84 becomes this y. And this gives me this equation, okay? But so far, that only solved the underlying independent weights, V. This gives me the best ridge regression for V. But I don't want to work with V, I want to work with W, because I want to find the weights that can be directly used on my original data X. So I have my V, I plug that in. Since the W is defined by this equation, so I just plug that in. This looks complicated, but it looks complicated. It truly looks complicated, but it's actually not that daunting. So this term, you want to go into this minus inverse, right? So you just multiply it, because minus half, because once you have that, once you take the minus, the inverse, when you take it out, it becomes positive half. When you get into the inverse, you get this into this bracket, okay? There are two terms, one into this, one into this, so that becomes this. So I color coded it so it's easy to see the effect of that. The other thing is I want to get this guy. This also have half of this sigma W into this bracket within this inverse. And then it becomes half of minus inverse. Likewise, this minus of inverse. Now I just need to cancel out all these terms. The minus half or positive half, these cancel out. Minus and positive, they cancel out. And then this and this cancel out because I is an identity matrix. So then what I have in the end, clean up is just these terms, okay? So this whole thing is reduced to this much simplified. And this I just copy over. Now you can see that this is a prior term. In my prior, I think that the W falls into Gaussian space with the mean of mu W and with the sigma W. Okay, the covariance sigma W. So the prior term is there. And this is data dependent. It looks at X, it looks at Y. So you can see the effect of the covariance of W, your prior belief on where the W should be like, goes into this conditioning factor, okay? The rest is what you have. This is just subtracted this because you add this to it. So this controls how the data fit affects the weight estimate. This we consider a generalization for rigid regression from this RID noise to this RID prior to generic prior, okay, in the weight space, not the noise, okay? This is called Tikhonov regularization. So this long complicated, the equation 88, if I look at the special cases, if it's 0 and I, it's a reduced rigid regression. It's simply this. If the weight is 0, but this is a diagonal matrix, we have some understanding. Otherwise, it's very difficult to calculate this. This will help us to see what the effect of covariance is on the weight estimation. When it's diagonal matrix, the inverse of that is just inverse of each the sigmas. The Tikhonov solution essentially says, if I believe one of the parameters have a very large sigma, okay, very large variance, meaning I'm uncertain, I'm not committed. For example, in the data, I think the slope could take a wider range of values, so I'm not committed to it. And then 1 over sigma I is very small, it's almost 0. So this will be effectively for that particular dimension, I just add a very small value to the diagonal of this data covariance matrix. So I do not inject much bias to the data covariance. I let the data speak for itself. But if the sigma is very small, meaning I already have a strong belief where that feature value should be, and then this 1 over sigma is going to be very large. So the data term may not matter as much. This term becomes dominating in this inverse matrix. Okay? So this is how we get the intuition. How does the generic prior influences our least square regression? So we have further generalization where we have map with both generic prior and colored noise. So these are both generic. And in this case, again, you use this reparameterization trick. Anything that's colored, you introduce ID Gaussian. For W, you represent with some matrix, RW times V. For the Gaussian noise, you have another RZ times U. These two sets are independent of each other, okay? They don't talk to each other. This is the noise space, measurement noise. This is in the prior space. And then y equals xw plus z becomes this. And I can write it out in terms of joint Gaussian random variables. One is y equals xw plus z. You see, in the end, the two variables is u and v. So u, I have to multiply with rz, this term. And this one, for v, I have to multiply with xrw. W is relatively simple, just rw times v, has nothing to do with u, okay? So now you can follow this derivation. In the end, you can come up with this generic Gaussian prior and a noise solution. It takes this form. Just take a moment to reflect on this. This is what we know. This is just denoising the data, whitening the data. Okay, you apply to x and y the data. The prior, the covariance of prior, takes its effect in this covariance, the data covariance matrix. You multiply, you bias, you add offset to it. Okay. Here we're assuming the mu w is 0. Okay. But this is a simple, it's easier to understand. So the last slide is this summary of what we have learned so far. You have this 2D layout. One is this noise model. You could have white noise or you could color noise. The weights you could have, if you had no prior, it's just ordinary least square solution. When you have added color noise, you have GLS, generalized least square. If you have independent but uniform prior, if you are dealing with white noise, you have rich solution. If you have color noise, you need to denoise the thing. It's a rich plus color. There's not particular name for it. And then if you have generic prior, if it's white noise, we have the Tikhonov regularization. And if you have this added effect of color noise, you have this more complete form where both in this table, you will have both the mu w added and the sigma w added to the covariance. So that's it for the linear regression. There's a lot of derivations, and some of this derivation for those of you interested, you should look into the notes. It's actually a pretty interesting way of